Welcome to Spectral Productions, where we take you behind the scenes in the making of our first independent computer animation production, The Last Ride. We're currently working hard on our proof of concept short film, The Last Ride Exposure. Today we're going to be talking about an anti-gimbal solution. So what is gimbal? Well, simply put, gimbal is when the rotational axes of your object line up with each other. When that happens, the object is unable to rotate in any other axes, and that is known as gimbal lock. When you hit gimbal, you sometimes run into a situation which I call Eulering. What that basically means is that the rotation becomes arbitrary, and the computer will sometimes have a bad job figuring out what is the correct rotation. As an example, if you take your rotation tool and set it to gimbal mode, you can see I can rotate in X, and it looks like nothing is changing. That is because X is the last to evaluate in the rotation order. The rotation order can be found here in the attribute editor, right here as rotate order. As I rotate in one of the other axes, you can see that the X and Z rotation line up. There is now no way I can rotate the arm forward and maintain a clean rotation. And you see here I am now at 6.8 and about 90 degrees in Y. As I try to rotate in Z, you'll see that the numbers suddenly snap to somewhere in the neighborhood of 90, 90, and 90. That's because there was no rotational axis to be had, and the rotations jumped. What happens sometimes is that it will get confused. For example, 90 degrees is the equivalent angle of minus 270. So sometimes when we get out of gimbal, the rotation that is picked is an equivalent value. This can often lead to problems when you are extrapolating between the two rotations. There's actually a function to help filter out Euler curves, which is known as the Euler filter. In this rough animation, where we see Daniel pushing Bethany away, you'll see that Bethany's hand IK flips around. If you look in here in the values, the Z starts at almost 200 degrees, but ends at minus 100 degrees. If you look at the curve editor, you see a very weird plateauing effect here in the Z curve. This is where the Eulering has taken place. At some point between this key, and from this key to this key, Maya got confused and spun the curve 360 degrees in the other direction. By applying the Euler filter, you see that the curve looks much cleaner. And as we scrub through the animation, the spinning no longer takes effect. So how does this apply to our rig? Well, we don't want that kind of Eulering happening in the rig as we're animating it. If you have a control structure that is Eulering and it's directly controlling another joint in the rig, you may have a tough time preventing that Eulering from happening. Your joints may suddenly pop into a different orientation or spin around. There's a couple things you can do to help prevent this. One is change the rotate order. However, I don't recommend this for a couple of reasons. First of all, if you have your control rig directly manipulating your bind, and you change the rotate order on your control rig, it may no longer drive your bind rig correctly. If it's being driven by a constraint, the constraint will force the joints to try to line up, but that too can cause it to hit the exact problem you're trying to avoid. More importantly, it's been my experience that human IK does not like a rotate order that is not the default XYZ. What I've done in my rigs is I've orientated the joints with Z out. This has given me the most flexibility in posing the character and the least likely to hit those kind of gimbal situations that caused the situation in the first place. However, avoiding Euler rotation and avoiding gimbal lock is sort of like avoiding death. You can dodge it for a while, but eventually you'll hit it. So what's my solution for this? As you can see here in the shoulders, as well as in the thighs, let's hide that for now, I've tripled up the joint count. I'll explain how this works in a minute. I first got the idea from a SIGGRAPH paper from Eric Miller and Rudy Grossman several years ago at GDC in Boston. In their lecture of Hyperreal Creature Anatomy Part 2, they describe a joint system where they use a joint chain driven by a spline IK to simulate the muscle mass coming from the trapezius all the way down the arm. This works well in film rigs. However, there are certain issues we had in implementing it as a game rig. Doing procedural animations such as in-game IK or ragdoll tend to break the system and make it not deform properly. However, it was enough to give me an idea to create a system of my own very similar to this one and use as much of the same ideas. What we're going to do is we're going to use a spline IK to split the rotations between these three joints. Since no one joint has the full rotation, it will be way less likely that we will ever hit gimbal. So this is my bind rig, so I'm going to start by duplicating these joints. I'll replace the joint suffix with a driver suffix on each of these joints. As I mentioned before, it's really important to have a good naming convention. However, what the naming convention is isn't nearly as important as the fact that you have one. And this one I will have, I'll call that the end. That'll be the end of my driver chain. Now I have this joint in the middle. I want to keep that. What I'm going to do is I'm going to duplicate that chain. And I'll slide that up a bit. And then I'm just going to reparent these a little bit and pull that sole joint out. So what am I going to do with this one? This one is going to be my roll driver. Connecting the translate is not technically necessary. However, it's handy if you want to add a stretchy spline IK to these three joints, and it does tend to help if they do stretch a little bit. It depends on the situation. Some rigs, it doesn't really make a difference. Other rigs I've had, it really helps maintain the system, the integrity of the system much better. Driver, thigh. Let's hook up the translate. Hook up the rotate. Now you can do the exact same thing that I did in the hypergraph with the node editor. There's the driver. There's the bind. Rotate to rotate. Translate to translate. No, we're still getting a bit of a pop there. Let's go ahead and kill those clusters and try it the other way. And this too is where not having it in 90 degrees would be more helpful. Again, the 90 degrees makes it easy to know where to line up our control rig. If it's got a kind of an arc, you kind of have to guess, but then you have to deal with this kind of problem. Create the cluster. Create that cluster. Parent it to there. And you can see it's no longer popping. It's still moving, but it's not popping. So I'm just going to take that roll driver and I'm going to parent it back underneath the thigh C driver. I'm going to create a simple RP solver with a pole vector. This little script is handy because it creates the RP for me, the pole vector, and names everything accordingly. But you could easily do that manually. So now I'll take the IK handle and the pole vector and parented it to the same control. Again, I shouldn't tell you that since my IK drives the same system, this works rather well. So now whenever this control twists in X, that driver will also twist in X as well. So now we have our roll driver, and we have one roll joint. I put in 2. Let's fix this. I am going to add another joint into the hierarchy here, because I want to have more than one roll joint. If you're doing a classic linear skinning, the more roll joints you have, the more smoother your twisting is going to be. If you're using dual quaternion skinning, it's less of an issue. But still, it might be good to have a second roll joint in there just to be safe. We'll talk about dual quaternion skinning, linear skinning, and blended weighting in a later episode. For now, let's just add another roll joint in there. So it goes, roll joint is 20, knee is 20. So let's go ahead and unparent that for a moment. And let's duplicate this. I'm going to set the first one to be 10. I'm going to set this one, I'll have this one parented to this one. Let's make them more like 12. That's a little closer to being even. We'll call it left thigh roll 1 joint and left thigh roll 2 joint. Oops. And then we'll put that knee back in there. Not too bad. So let's take that roll driver and these 2 roll joints. Let's create ourselves multiply divide node. There's a driver. Take the rotate X into input 1. For input 2, we can multiply it by 0.5. I could also divide it by 2. Take the output of X and put it into roll 1 and roll 2X. Now another thing I do is because this joint chain tends to not maintain its volume too much, so to compensate for that, I'll come down to the knee FK where it's connected to the knee joint. Now I'll just pop in a point constraint. That'll hold the 2 together. And again, our knee has a point constraint to it to help take up some of the distance, because you can see our end driver of our system is right there. Thank you very much for watching. Any comments or questions, feel free to post. I will answer as many as I can. I know that this rig is still a work in progress, so you're seeing it in a half completed state, which might be a bit confusing. Thank you for watching, and see you next time.